see in the figure how resonance is occurs. See here, graph of inductive reactance XL and graph of capacitive reactance XC. When both are intersecting each other, the intersecting point is representing XL is equal to XC, and it gives my resonance frequency. In previous part, my circuit is capacitive because capacitive reactance is more. In later part, when frequency is more than resonance, my circuit becomes inductive where XL is greater than XC. So in series resonance circuit, resonance frequency is given by 1 upon 2 pi under root LC. So we have to explain with the graphical notation and with the derivation. By two terms we can explain our series resonance for 3 or 5 marks. Okay, now it is a combined response of frequency with capacitor, inductor and impedance. See, graph A represent the inductive reactance is increasing, it is XL. Graph 2 is ZC. See, ZC is negative, so it is in negative quadrant. Now difference between XL and XC is representing by this line. So when this line is cross 0, it gives me cutoff frequency. That means here XL and XC both become equals. See, the upper part is XL and lower part is XC. So these both become equal, then this part is resonance. So here I get my resonance frequency, and impedance is represented by the graph D. So it is a relation of impedance with respect to frequency. Now what is the application of series resonance circuit? So in a brief, we see the application of resonance.
Today we are going to talk about resonance in AC circuits. This is something you actually use in your real life, because when you are tuning into a radio station, you are actually using resonance. Probably you know this, that a particular radio station transmits electromagnetic waves of a special frequency. So each radio station has its own frequency. Now while you turn the knob of the radio set, what you are doing is you are varying the capacitance of a circuit over here, and this in turn varies the frequency of the LCR circuit of the radio. Now when the frequency of the incoming waves from the broadcasting station match the natural frequency of the radio circuit, which is the frequency of this LCR circuit, then resonance happens. Now how do you detect that? That is the point at which the reception has maximum clarity and the current in the circuit is maximum at that instant. Now let's look at this a little in detail. If you recall, the impedance of an LCR circuit is given by Z equals square root of XL minus XC whole square plus R square. In case you are not familiar with this, I suggest you first go through the previous lessons, which is connecting an AC across a resistor, an inductor, a capacitor, an LCR circuit, and then come back to this lesson. Now coming back to this, the inductive reactance XL is given by omega times L, and the capacitive reactance XC is 1 over omega C. Now you can see that since both of them depend on the frequency omega, so the total impedance Z will also change with the frequency. See, if I draw a graph for each of them, now this is again something which has been discussed earlier, so in case you are not familiar, just go through it. This would be the graph for XL, since the inductive reactance is directly proportional to frequency. This would be the graph for XC, since the value becomes very low at high frequencies. This is not 0, it tends to 0. this is XC, and this is actually, the x-axis is actually an asymptote, so it doesn't really touch the axis. And the graph for the frequency would look like this, because the frequency doesn't change with, the resistance doesn't change with frequency. The total impedance Z, if I draw a graph, it would look like this. This is the value for, this is the graph for Z. And you can see that Z has a minimum value at a particular frequency, which I am going to call as F0.
Okay, so it is a F0 frequency, that is a resonance frequency. So as we discussed earlier, when XL and XC both are equal or both are intersecting, at that point we get our resonance frequency, or XL equal to XC, we get our resonance frequency. Okay, now next point, define the term time period, frequency, amplitude, peak factor and form factor. So 5 definition for a 5 mark. Let's discuss. The first definition is the time period. And what is time period? So time is taken by the alternating quantity to complete one cycle is known as time period. Time period is denoted by capital T and the unit is second. So let's understand by the one figure. See here, one alternating quantity is represented by this waveform. Okay, so time taken to complete the complete waveform is known as T, and it represented in second. That is a time axis. So time period is time taken by a quantity to complete one complete cycle. To complete one cycle, we require the time is known as a capital T, and unit is second. We have to write down the definition and we have to draw the figure also. Now second is frequency. Now what is frequency? The number of cycle per second is known as the frequency. Frequency is denoted by F. See, frequency is also denoted by F is equal to 1 upon T, and unit is hertz. So what is frequency? So that is a number of cycles in a given time period. Then frequency is also representing by 1 upon period or 1 upon T. So total time of 1 second, and there is a number of cycle is representing frequency. Now what is amplitude? The maximum value of alternating quantity, positive or negative, is known as amplitude or maximum value. See in figure, what is maximum value of alternating quantity? See, this is a maximum value. This represents the maximum value. So it is a if current, then it is a Im. If it is voltage, then it is a Vm. So maximum value is known as amplitude or maximum value. Either it is positive or either it is negative. It may be a negative maximum or it may be a positive maximum. So it is known as amplitude or a maximum value. Next definition is peak factor. The ratio of maximum value to the RMS value is known as peak factor. See, in the form of equation, the peak factor is the ratio of maximum value upon RMS value. As we know that the maximum value is Im and RMS value is 1 Im upon root 2. See in the figure, peak factor is given by maximum value upon RMS value. So maximum value of current is Im and RMS value is Im upon root 2. So Im cancel, it gives root 2, and value of root 2 is 1.41, and that's why we call that the value of peak factor is 1.41 for sinusoidal current. As we seen in the PPT, the maximum value of current is 1.41. Last definition is form factor. The ratio of the RMS value to the average value is known as form factor. Form factor equal to RMS value upon average value. Now, as we know that RMS value is Im upon root 2. See here, the average form factor equal to, as we know that the RMS value is Im upon root 2 and average value is 2Im upon pi. Im cancel, pi upon 2 root 2. After solving this we get 1.11. So value of form factor is 1.11 as seen in the PPTs. Okay, now last question is a 10 ohm resistor, a 15.9 millihenry inductor and 159 microfarad capacitor are connected in parallel to 200 volt 50 Hz supply. Calculate the supply current. Data is given for resistor, inductor and capacitor. We have to calculate the supply current. Total supply current is how much? So let's see in the figure. Here total supply current is Is. Now current flowing through the resistor is IR, current flowing through the inductor is IL and current flowing through the capacitor is IC. Data is given. Value of resistor is 10 ohm, value of capacitor inductor is 15.9 millihenry, value of capacitor is 159 microfarad, voltage is 200 volt and frequency of the supply is 50 Hz. Now we have to calculate what is the value of current. So now let's go for the derivation. Let's see in the OHP, R is given, L is given and C is given, V and F is given. So first we have to find out the inductive reactance XL equal to 2 pi FL. So 2 pi, frequency is 50, inductive reactance is 15.9 into 10 raised to minus 3. The calculation gives the simple answer 4.999 and it's a near about 5 ohm. So inductive reactance is nearly 5 ohm. Now we go for capacitive reactance, 1 upon 2 pi FC. So 1 upon 2 pi, frequency is 50 and C is 159 into 10 raised to minus 6, and after solving we get the value of XC is 20 ohm. So now two reactants are here, XL is 5 ohm and XC is 20 ohm. Now we find out the current through each branch and then we go for the total current. So current through resistor is IR, it is given by V upon R. So voltage is 200 volt, resistance of 10 ohm, so total current is 20 ampere. Now second, current through inductive branch. Current through inductive branch is given by V upon XL. So again 200, as we previously derived, inductive reactance is 5, so answer is 40 ampere, and capacitive current IC is V upon XC. So V is 200 and capacitive reactance is 20, so answer is 10 ampere. Now we get three current IR, IL and IC. Now addition of these three current gives us total current, but inductive current and capacitive current both are the out of phase, and so we have to take a difference between them, and therefore we take net reactance or reactive current, net reactive current between these two current is 40 minus 10 equal to 30 ampere. As inductive current value is large, we call that our circuit is inductive. That means inductive reactance is more here, so circuit becomes inductive. And now finally we go for the value of total current. So total current is given by IR square plus IX square. IX is net reactive current. So value of IR is 20 square plus 30 square. By solving this we get 36.05 ampere. It is value of net reactive current, 36.0.5 ampere. So with this question we have completed our paper of January 2012. Thank you very much, and I wish best of luck for your examination. Thank you very much.